So this is a projection, a bunch of spaghetti models for Hurricane Ike a bunch of years ago. We just looked at one for Hurricane Irma. But the point is, in working on these projections, trying to figure out when a hurricane is going to be at one place versus another, you have to figure out how long these curves are. If you're just going to do something simple like distance equals rate times time, well, what's the distance? And then, of course, you can figure out the time. Because they're curves, you can't exactly measure them very easily in a straightforward way. You're going to use calculus. So I'm just going to give you kind of a quick rundown of what you would have to do in order to calculate these. And it's going to enlighten us as to the formula. One way that you could approach the idea of trying to find the distance along the curve is to break it up into little segments here. So a straight line here, a straight line here, and then add up all these straight line distances. Now these straight line distances you would calculate using the distance formula. X2 minus x1 squared plus y2 minus y1 squared, etc. Like this. So add all those up, and that would be approximately your arc length. And for whatever reason, I think it's probably because physics uses it, we use S to represent arc length. Now, let's play around with this a little bit. This distance, we'll call it delta x sub I. So the distance between the x coordinates in that interval, and similarly speaking, delta y sub I. Both of those are squared. And then we're going to play a little game here. We're going to factor out this delta x sub I right here from both of these terms. And when you take the square root of that, you'll have a delta x sub I on the outside. This is still approximation to that arc length. But now what can we do to make our approximation better? Well, we can take the limit as these little arc lengths get very, very small. And as you take that limit, you're going to pass from a Riemann sum into an integral. And with a little bit of work, including perhaps the the mean value theorem, you can replace this and this down here with this limit and down to here. So this is going to be our formula for the arc length of a function between 2 points A and B. So this is the one that you should be familiar with and know and use for your exams. So it's the integral of the square root of 1 plus the derivative of your function squared dx between A and B. There's a similar analogous formula for arc length if your function is defined in terms of y as opposed to terms of x. But let's practice this with a couple of problems, starting with number 10. The thing about this that I'm not a big fan of is that a lot of times, in order for these things to come out nice and neat, the problems have to be somewhat contrived. And I'm not a big fan of that. So one of the things we'll do along the way is work on setting some of these things up and then finishing off with numerical integration. And I don't think I've been shy about using numerical integration here, nor telling you that I expect you to be able to do some numerical integration. All right, so there, oops, where's our image? There we go. We'll start with problem number 10. Y equals 3 halves times x to the 3 halves, no, let's see, x to the 2/3 plus 4. And we want to find the length of this curve between points 1 and 27. So let's just write that here, 1 and 27. The first thing we're going to need is the derivative here. So y prime. Y prime works out pretty nice. What is y prime on this one? Come on, make me look it. All right, well, this and this are going to multiply. What happens when you multiply 3/2 times 2/3? Cancels. You're going to get 1. And then if you subtract 1 from this, you get negative 1/3. What's the derivative of a constant? 0. So there's your derivative. X to the negative 1/3. Okay. So let's set up the integral to find the arc length of this curve over this interval. So that'd be the integral from 1 to 27 of the square root of 1 plus f prime squared. Well, this is my f prime of x. So I want x to the negative 1/3 squared dx. And now this is your basic setup. So hopefully you can get here without too much trouble. The rest of it I'll show you is going to be some little tricks in terms of integration. It's not going to amount to anything more than a u substitution. If I square this, what happens with the exponents? They multiply. So it's going to be x to the negative 2/3. Still have that dx there. Let's keep going. What I'm going to do is I'm going to try and add these things together. I'm going to need a common denominator to do that. Now, this term you might recognize as 1 over x to the positive 2/3. And in order to add these things together, I'll write this as x to the 2/3 over x to the 2/3. Well, I've got common denominators, so I can add the numerators, and I'll get the interval from 1 to 27 of the square root of x to the 2/3 plus 1 over x to the 2/3. Now here's the nice part. We can actually break this up into 2 square roots. Square root of the numerator and square root of the denominator. Square root of the denominator is going to work out pretty nice and even. Square root of the numerator, not so much. Not yet. Square root of x to the 2/3 plus 1 over something. What do I get when I take the square root of x to the 2/3? Yeah, x to the 2/6, and in lowest terms, that would be x to the 1/3. X to the 1/3. Now to help things out, let me rewrite that like this. 1 to 27, x to the negative 1/3, square root of x to the 2/3 plus 1 dx. It doesn't look like we've gotten far at all. We've done about 4 steps, and it feels like, gosh, where's this going? Well, in actuality, rewriting it like this has helped us out. We can now finish this up with stuff that you know. We're going to do a u substitution. Right now, u substitution is really the only good thing you've got in your bag of tricks to integrate things. So, what could I let u equal? Suggestions? There you go. X to the 2/3 plus 1. If we let u equal this, this is going to be part of my du term. And that's always the key when you're trying to find a u substitution. Part of the integral has to be the derivative of the other part. And that's what's happening here. Because when I calculate du, I'll get 2/3 x to the negative 1/3 dx. And I've really done 2 kind of steps here. Let's see what I've got here as compared to the integrand. I've got x to the negative 1/3, good on that, and I've got dx, good on that. So let's do ourselves a little favor and get rid of that 2/3. How can I get rid of that 2/3? Multiply both sides by the reciprocal. So this is going to be 3/2 du equals x to the negative 1/3 dx. So great. Now I can make a nice one-for-one change. Let's see. What else should I do while I'm here? Perfect. Let's change the limits of integration here. So if I put in a 1, u of 1 is going to be 1 to the 2/3 plus 1. I'll get 2. Nothing big there. Now u of 2, or excuse me, not u of 2, u of 27, well, that might require a little bit more thought. 27 to the 2/3 power. So 27 to the 2/3 power plus 1. Well, yes. If you can't see that it's 9, there's a couple things you can do. You can do it on your calculator if you're a little bit careful. Or you can remember that there's an equivalence between radicals and exponents. So let me remind you of that. I always suggest people use the boot method. You take advantage of your natural aggression to the subject of math, and you kick this helpless little denominator, which comes flying over here, leaving nothing to support the 2, which falls down. You get the cube root of 27 squared. Let's do the root part first. What's the cube root of 27? 3. So that'll leave you with 3 squared plus 1, which is 10. So those are your new limits of integration. 2 and 10. Let's finish this up. That's the integral between 2 and 10 of the square root of u times 3/2 du. The good news is that we're done with x. We don't have to go back and change units and work with x. We're just done with it. I am going to clean this up a little bit. Let's take the 3/2 out in front and rewrite the integrand. How am I going to rewrite the integrand? Good. U to the 1/2. Okay. When we integrate this, you add 1 to the exponent, 3/2, u to the 3/2, divided by 3/2, between 2 and 10. And there's even more good news, right? What's the good news here? Yeah, 3/2 and 3/2 cancels out. So it's just this last part here. It's going to be 10 to the 3/2 minus 2 to the 3/2. And you might be able to cleverly figure out something to do there, but you know what? I'm not really interested in that. This is a good final answer for me. It's a nice exact or closed expression. Okay. So, you know, a little bit of a grunt work in there, but overall, it's just an application of that simple formula. Square root of 1 plus f prime squared dx. And this is some good practice. Change your units, doing your u substitution for integration. How are we looking on that first one? Problem number 10 there. Section 7.4. On the exam, I limit myself to no more than 12 of these. Okay. Now, yeah, I try and keep them reasonable. And, you know, one of the reasons I keep on emphasizing numerical integration is because that's a way I can shorten this problem. And that, to me, it feels a little bit closer to, you know, what's going to happen when you leave, you know, college or universities. Is that you're going to start doing these things on, you know, computer-aided design machines or things that are going to have built-in functions. But what you are going to have to do is set them up. So, yeah, it's great if you go to Wolfram Alpha, it'll find an antiderivative for you. But what do you put in to start? you have to give it the right thing to start. And that's where I'd like to leave you off, is make sure that you can at least put in the right thing to start. Okay, other questions on problem number 10? Let's try problem number 12. Y equals the natural log of the cosine of x. And we're going to work on the interval 0 to pi over 3. I like this one. It works out really, really good. Let's remind ourselves of something first before I really get going on this problem. The one Pythagorean theorem identities you need to know is this one. It's sine squared of x plus cosine squared of x equals 1. That one you should know cold. Now, personally, I've been teaching calculus, statistics, trig, etc. since 19 mumble, and I still don't have all the different versions of this theorem memorized. Whenever I need them, I derive them. So what do I mean? Well, what if I took this and divided everything through by, say, cosine squared? Yeah. So now you get another identity. Tangent squared of x plus what? 1 equals secant squared of x. If I divided this through by sine squared, I get another identity. If I move the 1 to the other side, I get another identity. But there's so many things you can get just by working with this one identity. All right, so that's kind of a little, no pun intended, but tangent for us here, right? Let's go back and figure out the arc length of this thing. And it's going to start by finding y prime. Ooh, here's a good one for you. Oh yeah, logarithm. What's the derivative of the log function? Yeah. So, as a reminder here, d by dx of ln of u. When you differentiate the log function, you get 1 over u times the derivative of u. What's that going to look like here? Yeah. So you'll start out by getting 1 over cosine of x times the derivative of cosine x. What's the derivative of cosine x? Negative sine of x. Can anyone simplify that for me? Thanks, Hans. Negative tangent of x. Thanks, Hans, and a few others there. Okay, great. That's all I needed. Let's put it in and find an integral that reflects the arc length of this curve. So, integral between 0 and pi over 3. See if you can't fill in the rest. So, without looking up here, see if you can't fill in the rest of this integral. What's it going to look like? Okay. Actually, this, well, you know what? It is squared. The squared should be on the outside, though. My bad. All right. Now, when you square this, when you square something that's negative, it becomes positive. 0 pi over 3. So 1 plus tangent squared x dx. So remember that tangent of x squared is the same thing as tangent squared of x. It's just a notational convenience that we allow ourselves here. This actually works out really, really nice. So, who was it, Sandra? I was worried about, are you going to get them all this long? Here's a nice one for you. All right. That wasn't Sandra. Oh, yeah. All right, good. So So this one actually works out pretty nice. Can you see how or why? Oh, yeah. This 1 plus tangent squared is secant squared. So isn't that special? 0 pi over 3 square root of secant square root of x dx. Okay. Yeah, you get rid of the square root and the square root. Those two operations cancel each other out, right? So it's just the integral from 0 to pi over 3 of the secant of x. Well, that's not too bad. The integral of secant of x is something we learned in Calc 1. Right? Mumble, mumble. Anyone? Natural log of the secant of x plus the tangent of x, log of secant of x plus the tangent of x between 0 and pi over 3. Yay. So ln of secant of pi over 3 plus tangent of pi over 3 minus the ln of the secant of 0 plus the tangent of 0. Now, at least with the second of these, we're going to get some nice simplification. What's the tangent of 0? 0. So that's a 0. What's the secant of 0? That's a 1. And what's the log? So I got 0 plus 1. What's the log of 1? 0. So that whole thing disappears. Well, that's nice. I like that. Sandra's happy. Oh, good. Got rid of that. All right. How about over here? Now, if you're struggling, going, oh man, I just don't remember those things. Look, you can do it on your calculator. There's nothing wrong with taking that thing out. Secant, it's going to be 2. But how would you do that on your calculator? Put your calculator in radian mode, and we do 1 divided by cosine of pi over 3. And it should give me 2. Yeah, 2. What about tangent? Tangent of pi over 3. Well, tangent of pi over 3, let me think here. What would it be? Square root of 3? Yeah. Now, you might not recognize it, but one thing you can do to help yourself recognize that is hit the square button. Oh, that's 3. So I guess I started out with the square root of 3. So what you end up with is the natural log of 2 plus the square root of 3. Nice. If I ask you for an exact answer, this is what I'm looking for. Sometimes I'll ask for decimal answers, in which case you can use fn int to finish that one up. But this one worked out pretty nicely. Let's try 24, unless there's some specific questions on this one. Yes, sir. Brandon.
I had a hard time just remembering that step that we were supposed to know in Calculus 1, taking that secant squared and taking the integral of that down below. Like
this one?
Yeah, that step.
Oh, the antiderivative of this? Yeah, I mean, that, I think I've promised this class I'm not going to get anything really obscure. So the obscure ones in my mind would be some of the hyperbolic ones, like the hyperbolic cosecant. Cosecant in general, I kind of avoid those. But I think there's a good list of your integrals, your basic integration formulas on the inside cover of your book. So you might want to refresh yourself here, right here. I guess the only one that I don't really see myself using is number 20. Let's see, 20, 17, I don't typically deal with this one. 15, again, cosecant. 13. It's not that these are bad. Cotangent, you could actually almost derive that one. It's just a u substitution. If you regard cotangent as being cosine over sine, it's just a u substitution. So this one's not too bad. You could do that one for yourself in a pinch. But I tend to stick to the more typical ones. Okay. Anything else on this last one? All right. Keep your calculators handy for this next one. Does anyone need to borrow one today? The Calculator Workshop Loan Program is open for business. What's that? Keys or major credit cards? Thank you. Here, there's a cover for that. Thank you. All right. One more. There you go. Problem 24. Y equals ln of x on the interval 1 to 5. Again, you're asked to find the arc length. So what we're going to do this time, that's going to be a little bit different, is do this with fn int after we get it set up. But you help me with the setup. Let's start with y prime. So what's y prime? 1 over x. Good. See if you can't set up the integrand. All right, we know the formula for arc length. See if you can't set up that formula for this particular problem on this interval. No peeking. All right, here, we'll do it this way. There we go. Manual pause. You got it? Got it written down? What's that integral going to look like? Good. 1 plus 1 over x squared, square root of that, between 1 and 5. Now, depending on what kind of calculator you have and how up-to-date your operating system is, it should look like this. So hit the math key, then option 9. I can just type things in directly. It gives me a nice integrand. So 1 to 5. I need to start out with the integrand. So square root of 1 plus 1 divided by x, and then hit the square key. And last but not least, you're going to have to put in the x there at the end. It wants to know what integral or what variable it's integrating with respect to. If you have one that's old school, you can't do that, then it's probably going to look more like this. Fn int, left parenthesis, square root, another left parenthesis, 1 plus 1 divided by x raised to the second, right parenthesis to close off the square root, and then, let's see, comma x, comma 1, comma 5. That should give you the same thing that we got, about 4.367, 489, etc. Are you able to get that on your calculators one way or another? If not, Mimi will help you out. She taught me everything I know about graphing calculators. All right. Just kidding. I'm just trying to put you on the spot. That's all. Typically, I'll ask for 4. On the test, I'll tell you where exactly I want it rounded to. So if we're rounding to the 4th decimal place, this would be approximately 4.3675. Thanks, Sandra. Let's see. Let's take a little trip down memory lane here. Before we do problem number 32, let's remind ourselves of cosh of x. Certainly the hyperbolics are something that we covered in this course, and hyperbolic cosine in particular can be defined like this: e to the x plus e to the negative x over 2. Okay. In a similar way, hyperbolic sine, aka sinh, is e to the x minus e to the negative x over 2. And if you notice, one is the derivative of the other. The 2 is a constant, so that comes out in front. When you differentiate e to the x, you get e to the x. The only thing that's going to change is when you differentiate this, you're going to have the negative 1 that's going to multiply this sign in between. So 1 is the derivative of the other. Now I mentioned that in advance of problem number 32, which looks like this. Y equals 31 minus 10 e to the x over 20 plus e to the negative x over 20, like that. Okay. Well, before I really get going in working with this, let me rewrite this. And my inspiration here comes a little bit from these formulas. Now, which one does this look closer to? A sinh or a cosh? Cosh. Looks closer to cosh. So if I rewrite this as 31 minus, let's see, if I want this to be a cosh, that's got to have to be something over 2, right? E to the negative x over 20 over 2. But how would I have to change this to get away with writing a 2 here? Yeah, if I write that as a 20, because the 2 and the 20 will cancel. Nice. 31 minus 10 here, and it's 31 minus 20 here, because I got the 2 that'll cancel into the 20, and that would give me my 10. Now, why did I do that? Well, because this I can rewrite as 20 times something. And that 20 times something would be cosh of x over 20. So it's a nice trick to put this into a form of something that we can work with a little bit easier. Let's keep going with this one, and that's my y. Let's see if we can't figure out what y prime is. I'll give you a second to work on that. So go ahead. Figure out the derivative here. Make sure that you use the chain rule. I wouldn't look up here at this. Just differentiate it from cosh. Okay. What's the derivative here? Perfect. So derivative of that's going to be 0, negative 20 times sinh of x over 20 times the root of the inside, which is 1 over 20. So just as you said, those are going to cancel each other out. And you'll be left with negative sinh of x over 20. Nice. All right, we're ready to put this into our problem. Let me show you briefly exactly what this problem is. It's to try and find the area of a roof. And so the roof is kind of a curved roof. Oops. So it's 100 feet this way, and its profile this way has this shape. So to find the area of that roof, what you're going to do is find this, the arc length, and then do what? Multiply by 100. Perfect. So you can find out how many square feet you would need of material in order to put a roof, or to cover that roof. Okay, let's go back here to our formulas. We're going to integrate this as part of our work in finding the arc length. Don't do that to me. There we go. One other thing that we should note here. This picture is going to help us in terms of our limits of integration. Where should we integrate from and to? Yeah, negative 20 to 20. You could get away with 0 to 20 and then double it. I'm just going to put in negative 20 to 20 to start with. So negative 20 to 20, the square root of 1 plus negative sinh of x over 20 squared dx. What happens to this negative when I square this thing? It becomes positive, disappears. So good. Thank you. 1 plus sinh squared of x over 20. How am I going to find that one? Yes, there is a formula / identity. So remember that one. Yeah, good. So going back a little ways, but a good reminder, kind of a just-in-time reminder, this is going to equal cosh squared right here. So this is a flashback here. I'll write it over here. Cosh squared of x minus sinh squared of x equals 1. That is the one and only identity I asked you to remember from section 5.8 or 9, whichever one it was. And here again, we're using that. So, perfect. Just-in-time identity. And that becomes integral from negative 20 to 20 of cosh squared x over 20 dx. Well, that's going to simplify even further. How does that term simplify? Just cosh x, right? Integral from negative 20 to 20 of cosh x over 20. We probably could have done it earlier. We can certainly do it now. But cosh is an even function. You have an even function over a symmetric interval. So what we can do is we can double this and go from 0 to 20 of cosh of x over 20. You can take the time to make a u substitution. It's nice if you can start looking at these things and kind of working around the u substitution, figuring out, well, what would I have to do to adjust this? Now, let's think about it this way. If you were to differentiate this term, when you differentiate the inside term by applying the chain rule, you'd end up dividing by 20, right? Or multiplying by 1 over 20. So when you integrate, the opposite has to happen, right? What's the opposite of dividing by 20? Multiplying by 20. So 20 times 2 is going to be 40. What's the integral of hyperbolic cosine? I don't think there's a negative. I think it's just hyperbolic sine. You can take the time to do a u substitution. You'll get exactly the same place. And if this is too much mental gymnastics here for you, that's fine. Slow it down and do a u substitution. Either way, you're going to end up here. We're going to want 40 times hyperbolic sine of 20 over 20, which is hyperbolic sine of 1, minus the hyperbolic sine of 0. I don't expect you to remember all these things and be able to calculate these things. I do expect that you can find them off your calculator. So let's refresh ourselves on how to find the hyperbolic sine. Does anyone remember where it's at? Catalog menu. Good. So second, catalog. Do yourself a favor and jump down to the S's by typing the letter, or excuse me, typing the number ln. That'll jump you down to the S's. And then you can scroll down from there. You know what? We don't want S's. Yeah, we do. Yeah, we do. So, sinh. There we go. Sinh of 1. And then if you hit the second key and the enter key, it'll bring back your previous calculation. Now let's just go in there and swap in a 0, and it gives you 0. So basically, it's 40 times the sinh of 1 is your exact answer. And if I come back up here, sinh of 1 times 40. So, second key, then enter, will bring up your previous calculations. And if you hit second key and enter again, you can keep on scrolling further back so you can get older and older calculations. So it's kind of nice. You don't have to type in everything all over again. You can try and take a shortcut. So the length of the roof one way is 47 feet and some change, 47.008. So the area of the roof is that times 100. It's about 4,701, roughly speaking, square feet. Hans? Where did I get sinh of 0? Oh, I already had sinh of 1 programmed in, so let me... Oh. Right up here. So when we put in the limits of integration, 20 over 20 gives you 1, 0 over 20 gives you 0. All right. That's all right. Anything else on problem 32 here?